This is an overview of Chapter 14, Kinetics, and we're going to take a look at just an overview of the chapter in this first portion. In the second portion, we'll take a closer look at reaction mechanisms, some examples in practice, and then lastly, we'll take a look at some of the practice test materials and some multiple choice and some actual written problems that you'll have to attempt over the next few days. Chapter 14 is called Kinetics. Kinetics has to deal with the rate and the process of a chemical reaction. The reaction rates are factored by four different things. First of all, concentration of the reactants. Second of all, temperature of the reactants. Third of all, by the presence of a catalyst. And lastly, by the nature of a reactant. By that we mean whether it has a lot of surface area, very small surface area, whether the substances are mixed together in solution form, whether they're mixed together as solids, etc., etc. A lot of this chapter has to take a look at how concentration affects the rate of a reaction. And mathematically, we can take a look at how concentration affects the initial rate of a reaction by taking a look at something called the rate law. And the rate law for a particular reaction, that would be, for instance, A plus B goes to some product C, would be written like this. Rate is equal to some constant K times the concentration of A to some power X times the concentration of B to some power Y, where X and Y are called the orders, not the exponents, but the orders of each reactant. These brackets right here mean concentration in terms of molarity. Remember, molarity is equal to moles divided by liters. And the K right here is known as the rate constant. And the rate constant is dependent upon temperature, and it's also dependent upon what reaction you're doing. But the rate constant is very temperature dependent, and so depending on what temperature you're at and depending on what kind of reaction you're doing, you'll have a different rate constant. The rate is usually measured in concentration, so molarity, per unit time, so seconds or minutes or hours or something like that. And generally, units of molarity per second or molarity per time are written with negative exponents, and so it's written as molarity times seconds to the -1. These concentrations, of course, are given in units of molarity, and the orders of the reaction, once again, are just the exponents, so they don't have units. The rate constant also has units, and it depends on what the units of concentration are here and what the orders of the reaction are, and, of course, what the rate concentration is as well. Solving for the orders of reaction, or the exponents, allows you to find what's called the overall order of a reaction. And the overall order of a reaction is equal to the addition of the exponents of all the reactants that are in the rate law, or the rate expression. When you add them all together, they give you the overall order of the reaction. So concentration is a big thing that affects the rate of a reaction. There are three very normal or common orders of reactions that we see. There is a zero order, there's a first order, and there's a second order. 0, 1, and 2 orders of reaction. And when I talk about the orders of the reaction here now, they're pretty much the overall order of a reaction. And in this class, we generally just look at the three orders of a reaction with respect to one reactant. So let's take a little bit closer look at those in terms of zeroth, first, and second order of reaction. When we do this, the rate law for a zero, first, and second order reaction take on this form. Rate for a zero is rate equals some constant K times the reactant A to the 0 power, For a first order, it would be rate equals some constant K times the reactant A to the first power. And you don't necessarily have to put the 1 up there because it's always assumed that it's there. And for a second order, it's rate equals some constant K A to the second power, or to the second order. Now, a mathematical operation can be performed on each one of these equations. And the mathematical process is called integration. And when you integrate each one of these, you get a new equation. And each one of these is called the zero, first, or second integrated rate law. And you can use these when they're integrated with respect to time to determine the time at which a certain substance has a certain concentration. And the integrated rate law for a zero-order reaction is concentration of A is equal to negative kT plus the concentration of A original, or A naught, sometimes it's called. For first order, it's the natural log of the concentration of A is equal to negative kT plus the natural log of the concentration of A original, or A naught. And lastly, for a second order reaction, when it's integrated, it is the concentration of A at a particular time is equal to positive kT plus the inverse, or 1 over the concentration of A original. These are the integrated rate laws for zeroth, first, and second order reactions. Now, what's unique about each one of these equations is that if you look at it real close, they're all written in the form of y, each one of these representing y, equals m, each one of these k's representing m, or the slope, and x, notice time is x on each one of these, plus b. And you can say that this is an equation form for a straight line. Notice in the zeroth and first order, they're lines with a negative slope. And in the second order reaction, it's a line with a positive slope. And if you graphed each one of these, I'll put a title here for graph, and you graphed them y-axis, vertical axis, concentration versus time for this one, natural log of concentration versus time, and for this one, 1 over concentration versus time. For a zeroth order, you would get a straight line. Whoops, I'm sorry, I wrote that wrong. The zeroth order, you get a straight line in a negative direction, in a negative slope direction, because notice there's a negative slope right here. For first order, you would also get a straight line in a negative direction, but notice it's a plot of natural log of concentration versus time. And for a second order, if you graphed 1 over concentration versus time, you would get a straight line in a positive direction. So you can tell what order a reaction is simply by graphing its concentration versus time in one of 3 different ways. Now, the last thing that's kind of interesting about these zeroth, first, and second order integrated rate law equations is you can take each one of these equations, you can solve it for an interesting time. The interesting time that we want to look at is when does, in terms of time, half of the original amount exist? Half of the original amount exist. So technically what would we be doing is replacing each one of these concentrations of A's with the concentration of A naught divided by 2. Here the concentration of A naught divided by 2. Here the concentration of A naught divided by 2. When you do that, you've got A naught 2 places in the same equation. And you can go ahead and you can solve in terms of time. Now, if you want to see the total derivation of first order and second order integrated rate law is solved for half of the concentration. In other words, when time it indicates that there's half of the original concentration left. You can check it out in your textbook. But here are the results. The results are technically called the half-life, because it's when half of the original amount is still remaining, half-life equation. Okay? For a zeroth, a first, and a second order reaction. For a zeroth, T1 half, or the half-life, is equal to A original divided by 2K. For a first order, T1 half is equal to the natural log of 2 divided by K. And for a second order, T1 half is equal to 1 over K times A naught. Notice A first-order integrated rate law, when solved for its half-life, or for when half of the concentration, when it's half as much as when it began. It could be concentration, it could be pressure, it could be amount of particles as well. It's independent of the original amount of A. Independent of the original amount of A. Now, next in this, we'll take a look at how temperature affects a rate. These equations are used to determine how concentration can affect a rate at a particular temperature, because remember, K will change with temperature. And you can solve for a particular time, or you can solve for, if you know a time, how much of something will be left, depending on whether it's a 0th, first, or second order process. So next is temperature. Temperature affects the rate of a chemical reaction. As you increase the temperature of a reaction, the reaction goes faster. You can see by this graph of temperature versus the rate constant that as the temperature increases to the right, the rate constant also increases. As the rate constant increases, the rate of the reaction goes up. It's exponential. Temperature is directly related to kinetic energy. As a matter of fact, that's the definition of temperature, is that the kinetic energy of the gas molecule particles, or of any particles, increases, the temperature increases. And so as you increase that amount of energy, you can see that the fraction of molecules needed to get a certain amount of energy to make the reaction occur increases. Let's take a little closer look at this graph. Right here, this dashed line indicates the amount of energy that's needed for a reaction to start occurring. This is actually called what's known as the activation energy, and we'll come back and talk about that in just a second. The blue line right here indicates a lower temperature, and you can see that there's only a certain amount of particles right here that have enough energy to break that activation energy barrier, or this dashed line barrier. But as you increase the temperature, now you get to this red line. And notice the red line right here has way more molecules that break this activation energy barrier, and therefore there's more of them with the amount of kinetic energy needed to start the actual reaction or make the actual reaction occur. We can graph this another way as well. As we increase the amount of energy, we can graph it versus what's called the reaction pathway, or the way that the reaction occurs. This reaction right here is the beginning. As we add some energy to get this reaction going, the amount of energy increases, and eventually we reach the amount of energy at the top of the activation energy hill to say that we've got enough energy to activate or cause the reaction to start to happen. This is called the energy of activation, and it's symbolized by E sub A. Once you reach that amount of activation energy, then the reaction begins, or it actually runs. And you can see in this case, it runs and runs and runs until we actually end up with less energy than we started with. And so you can see here that we have a change in amount of energy for the beginning of the reaction to the end of the reaction. And you can see that it would actually be a negative amount of energy. We'd say that this would be an example of an exothermic reaction. An exothermic reaction, remember, is one that gives off energy. If this activation energy hill actually ended right up here and quit right here, then we'd say that the amount of energy at the beginning and the end actually decreased. Okay, and you can see here that we have a higher amount of energy at the end than what we started with. And so we'd say that our enthalpy, or our energy of reaction, would actually be a positive value, and it would be a endothermic reaction. Now you can look at this reaction in reverse as well. And let's say that we started right down here, and we ran the reaction this way, and we said that this was the end. Now to find your activation energy, you'd actually be looking from here all the way up to the top, and the activation energy would be greater moving this direction in the reverse. Now to make a reaction occur, you have to have collisions that occur. And the collisions that have to occur actually have to occur in the correct orientation,
and they have to occur with enough energy. And you can see that there are actually like individual steps that occur to make the reaction happen. And in the next section of the video, after a little bit, we'll talk about each of these individual steps, and we'll call them elementary processes or elementary steps that cause effective collisions to occur to make a reaction actually happen. Well, years ago, there was a scientist named Svante Arrhenius that came along and said, hey, how can we relate the rate constant to the amount of activation energy, and how can we actually calculate this activation energy? Well, to do this, he came up with what's called the Arrhenius Equation. And in this equation, you can take the natural log of K, and remember this is the rate constant, and set it equal to something called the frequency factor, which actually takes into account how many effective collisions you will have in a particular reaction. And over here, take into account the temperature, and the temperature in this case has to be in Kelvin. And here is the universal gas constant, and the gas constant in this case has to be 8.31 joules per mole times Kelvin. Notice it has to use the 8.31 for this. And right here, E sub A stands for the energy of activation. Now, solving this equation isn't extremely important in advanced placement chemistry, but understanding the setup of this equation and understanding what it represents is ultra important. Notice this equation is written in a specific format. This term right here is technically like a y. This term right here is m. This term right here is x. And this term right here is b. This equation is written in the form of y equals mx plus b, or a straight line. And so if you were to graph this equation or represent it graphically, you would actually say that on the vertical or y-axis, you would graph the natural log of k, or the natural log of the rate constant, and on the horizontal axis, you would graph 1 over temperature, or the inverse of temperature. And with this, you would get a line that has, notice here, a negative slope. So it would look something like this. The slope of the line would actually be equal to E sub A divided by R, but R is a constant. So technically, it would be directly related to E sub A. So one way to determine the activation energy of a reaction is to graph the natural log of the rate constant versus the inverse of the temperature. Notice the temperature is on the horizontal axis, natural log of the rate constant is on the vertical axis. This is known as the Arrhenius equation and is given to you on the equation sheet that you can use on the AP exam. Let me zoom in on it here. Notice the form that it gives in the equation sheet is the natural log of K is equal to E sub A over R times 1 over T plus the natural log of A. The y-intercept, this is the x-axis, this is the y-axis, and this, of course, is your slope. So this equation is given to you, and you just need to be able to understand that, hey, this is how the rate constant and temperature are related to each other, so you can find the slope of the activation energy. Another interesting thing to look at is the two other kinetics equations that they give you on the equation sheet. They give you the first order integrated rate law, and they also give you the second order integrated rate law equation. But they do not give you the half-life equations for each one of these, and you have to be able to solve for those. Notice they're in a little bit different format than what you probably saw in your textbook, but they are there and they're available for you to use. In this last portion of the video cast, we're going to take a look at some reaction mechanisms, some example problems, and some practice problems. And if you'd take a moment right now and pause the video and just take a look at reaction and find the reaction mechanisms, examples, and practice handout. This is located in your PowerPoint packet, or you can download it online as well if you're watching this at home. It starts right up here with reaction mechanisms, and it also gives a big table of some example reaction steps. So pause the video now and make sure that you've got this sheet in front of you so you can read it along with and fill out the notes as we go. Reaction mechanisms. Reaction mechanisms are processes in which reactants go to products and the steps that occur to make the overall reaction happen. There are several main rules that have to be followed. I like to think of it as two rules, but this kind of outlines all of the other things that add along with it. First of all, the stoichiometry, in other words, the coefficients of the elementary steps must match the exponents of the rate law for the slow or the rate determining step. The rate determining step is the slow step, the one that takes the longest to happen. Third rule, the intermediates may be used as long as they're used up at the end of the mechanism. And lastly, the rate law is only determined experimentally. It's only determined experimentally. Let's take a look at this sample reaction right now. You can see here that there's actually a little typo, and it says possible mechanisms for this reaction, and it should say this is possibility A, this is possibility B, and this is possibility C. And of course there's nothing here because it should all be shifted over a little bit, but it's a little easier to see now. And you can see for this reaction, if the mechanism is A, okay, where this is the slow step, this is the fast step, and this is a fast step, then the slow step would govern what the rate law would be. Notice there's a 1 in front of the A, so there would be a 1 above the A here as an exponent for an order. And there's a 1 in front of the B, so there'd be a 1 in front of the B or as an exponent right here. Okay? If you look at the mechanism possibility of being B, you can see we've got fast. Now here's the slow step. And so technically the rate expression should be B times X. So rate should be equal to the K concentration of B times the concentration of X. But the problem is that X is an intermediate. It's not in the overall reaction up here. So X can't be part of the rate expression. But since there's a fast step followed by a slow step, technically these guys right here, this X, is equal to the A and the B. The reaction actually backs up and causes these A and B to be equal to it. And just like in mathematics where you can use substitution to solve an equation, you can do the same thing with these mechanisms. A and B would actually fit in for X. So now your equation would technically be B plus A plus B goes to Y. Notice how I took this A and B and put it in here in place of X. Now my rate expression can match. Now my rate expression can match the stoichiometry. Hey, look at that, I wrote baby. Anyway, rate would then equal K times the concentration of B squared times the concentration of A. Two B's right here and an A right here. And that's what my rate expression is, 2 B's and 1 A. Now, let's say that the reaction mechanism was C. Well, if the mechanism was C, notice C plus Y yields D plus E. Okay? You'll notice Y is an intermediate once again. It's not in the overall reaction up here. And so you have to go back and you have to solve for X and B, and then you have to use this to go back X and solve for these guys, and so your rate turns out to be A times B squared times C. You can go back and solve that as well using the substitution, just like I did in this reaction as well. Note that the slow step and the previous steps are used to calculate the rate law. So it's the slow step that determines what the rate expression is going to be. Let's talk about elementary steps or elementary processes. A unimolecular step is one where you just have A going to some products. There's only one thing reacting. A bimolecular is where you have two things going and colliding together to make a product. For instance, A plus A or A plus B. Termolecular steps are quite rare, and this is where you'd have three things colliding exactly with the right orientation and making some types of products. Remember, these are quite rare and usually are just simply a multi-step mechanism. Multi-step mechanisms are sequences of elementary steps. They always have to add up to give the equation of the overall process. I think this is one of the biggest rules. And then, of course, the other big rule is that the exponents must match the stoichiometry. In other words, they have to match the coefficients that are in front of the reactants in the elementary process. It gives some examples of rate laws and elementary steps right here. And then it shows a termomolecular step here at the bottom. Let's go on and let's do some example problems now. I'll zoom in just a little bit on these. And then if you've got the sample problems along with you, you can, of course, read them a lot better than you can probably read them on the screen as well. First question says, it has been proposed that the conversion of ozone to O2 proceeds via 2 elementary steps. And you can see the 2 elementary steps right here. First of all, describe the molecularity of each step in the mechanism. This first one right here has one thing going to 2 others. And so I'd say that this would be a unimolecular step. Unimolecular. The second step right here has 2 things coming together and reacting, and so we call that a bimolecular step. Remember, the overall reaction, part B, would be the addition of these 2. And so if I took the things on the left-hand side of the reaction and added them together, and the things on the right-hand side of the reaction and added them together, I'll then get O3 plus O3 plus O goes to O2 plus 2O2 plus O. Notice I took all the things on the right-hand side and combined them together, and all the things on the left-hand side and combined them together. Now, if there are things that can be added together, go ahead and add them, and if there are things that can cancel, go ahead and cancel those. Notice there's an O on each side of the reaction. Those cancel out. And my reaction becomes 2O3 goes to 3O2. There's my overall reaction, the answer to letter B. And then letter C, identify the intermediate, if there's any. And in this case, my intermediate is the thing that exists for a moment, but it doesn't exist in the overall reaction. And which one is that? Well, it'd be the plane O right here. That would be an intermediate. So by knowing the molecularity and by knowing a little bit about steps in a mechanism, you can answer lots of questions about molecularity and overall equations and intermediates. Question number 2. Question number 2 says, if the following reaction occurs in a single elementary step, predict the rate law. And they've got the H2 plus Br2 goes to 2HBr. And if it occurred in a single elementary step, remember that the reactants then, the coefficients in front of them, would have to match the exponents or the orders for the rate law. So my rate expression then would be rate is equal to some constant K times the concentration of H2 to the first power times the concentration of Br2 to the first power. Still takes on the same form, but remember the coefficients of an elementary step have to match the orders of the reactants. If there was a 3 in front of here, I'd have to put a 3 up here because in an elementary step, the stoichiometry, the coefficient, must match the exponent. Of course, there's not a 3 there, so I can't put a 3 there. Next question. Rate laws with multi-step mechanisms. Slow steps limit the overall reaction and are called the rate-determining step. Example, a mechanism with an initial slow step. Write the rate law for the overall reaction that obeys the following 2-step mechanism. Here's step 1 and here's step 2. Now, if I'm told to write the rate law for it, I have to look at the slow step. Now, the stoichiometry, in other words, the coefficients, have to match the exponents. And my rate law would be rate is equal to K, concentration of NO2 to the second power. Why is it to the second power? There's no 2 in front of there. Well, there's an NO2 here, and there's an NO2 here. So since there's 2 of them, it becomes to the second power. Now, you could also write this as K NO2 times NO2. But remember, you just add the exponents then, and it becomes the same thing. Second of all, let's see if we can figure out what the overall reaction would be. What is the overall reaction for this? Well, remember, add the left-hand side things and add the right-hand side things together and put them together. So I'd end up with 2NO2 plus NO3 plus CO on the left-hand side of the reaction. And on the right-hand side, I'd end up with NO3 plus NO plus NO2 plus CO2. All right? Now, what cancels? Well, an NO3 goes away. One NO goes, whoops, I'm sorry, an NO remains. My bad. I meant to cross off this. NO2 goes away, and one of the NO2s go away. So my overall reaction is NO2 plus CO goes to NO plus CO2. This is my overall reaction. What did I do to find the overall reaction? Added up the left side of the elementary steps and the right-hand side of the elementary steps and put them together. Now, part B says propose a one-step mechanism for the above reaction. Now that I have the whole reaction, I could propose a one-step mechanism, and I could say, this is it right here. I could just say NO2 and CO collide. And then that would be my one-step mechanism. And I'd say that this is the slow step. I'd write the word slow after it, and that would be my proposed one-step mechanism. Okay, let's look at problem number 4 now. This is a mechanism with an initial fast step. Whenever a fast step precedes a slower one, we can solve for the concentration of an intermediate by assuming that an equilibrium is established in the fast step. This is what we did before in the example, right at the beginning, where I took and I said you could do substitution. Show that the following mechanism for the below equations produces a rate law consistent with the experimentally observed one. One that is second order in NO and one that's first order in BR2. So the observed rate law is rate is equal to some constant K times the concentration of NO to the second power times the concentration of BR2 to the first power. Okay, here's step 1, here's step 2. Now, if I just would write the rate law for the slow step, which is what I'm supposed to do, I would write rate is equal to some constant K times the concentration of N2O2 to the first power times the concentration of BR2 to the first power. But the problem is N2O2 is an intermediate. See how it's going to cancel out? Because there's one here and there's one here. But the good thing is that this is a slow step. And so really what I can say is that this N2O2 is equal to these two things right here. And so I can replace this in the rate expression and write it as rate is equal to K times NO to the second power times BR2. And by doing a replacement or substitution, some people call it, I can prove that, hey, this rate law, which you'd write from the slow step, is technically the same as what the observed rate law is. Hopefully you got a little bit of a look at some sample problems of how reaction mechanisms work. And you can do the rest of the practice problems now as your assignment for the next day. And I'd also like you to take a quick look at the practice test that's coming up. This practice test is also due on Tuesday, and you should attempt as much of it as you can. This practice test right here has a number of multiple choice questions. The test that's coming up in the next couple of days will actually be some multiple choice and some written as well. You can see that most of the questions on here are multiple choice, but a lot of the test questions will come both as multiple choice and written.